Okay, last example in our idea of basis. And before we get into that, we have a lovely little theorem here. This theorem says that we don't have to go through all of the trouble of arguing our way out of what the basis is for the column space of A. All we need to know is what are the pivot columns of our matrix. Those pivot columns form the basis for A, right? The pivot columns represent the non-dependent columns. So those are our independent columns. And so if we can figure out which are the pivot columns, we're good. And last but not least, we'll do a lovely, lovely bunch of coconuts. We'll go back and do our beautiful beautiful row reductions, all that fun stuff. All right, so here's my matrix. So on your own, however you want to do it, throw it in calculator, do your individual row reductions. Does not matter to me how you want to get there. But the simplest way to get there, so I don't have to actually do all the row reductions. I don't need to be in RREF form in order to make a statement or to decide what are my pivot columns. If I can get this down to 1, 3, -5, 1, 5, 0, 1, -2, 2, -7, 0, 0, 0, -1, 5, and 0, 0, 0, 0, 0. This is enough, so notice this is not RREF, but it is enough to be able to decide where my pivot columns are. So I've got, and remember your pivot points are anything in that row. It's got to be the first in the row. So I've got one there. I've got one here. Now I don't have one in the next column because there's a 0 and I already have a pivot point in the second row. So the third row, the first place that I have a starting position is at that -1. And the last one is a row of all zeros, so there's no pivot points there. So each of these is a pivot column, which means that the basis for the column of A, so our basis for the column of A is equal to the set. Now I'd be careful here. So it's the pivot columns. So it's not the pivot columns in our reduced matrix or in our equivalent matrix. It's our pivot columns from our original matrix. We're going to go back. We're going to decide, oh, hey, I have a pivot point in the first column. So that first vector is going to be in my basis. I have a pivot point in the second column, which means the second one is in my basis. And I have a pivot point in the fourth column, which means that this fourth column is in my basis. And that the other ones are redundant, right? So the other ones are linear combinations of the other, so I don't need to worry about them, right? Now for the null space of A, again, we got to take this a little bit further. And we also need to include that augmented with the 0, 0 space. So we do want to get this down to RREF form with our zeros in there. So if I take A augmented with the 0 vector, I'm going to get down to, and again, I'm skipping a lot of steps here because I know we know how to do the row operations, and that's neither here nor there, but we're trying to get a solution to this equation here, or describe all of the solutions there. So if I can get this down to 1, 0, 1, 0, 1, 0, 0, 1, -2, 0, 3, 0, bunch of zeros here. And we already know that everything down here was a 0. All right, so this tells me that, because we've already determined these are our pivot columns, that tells me that x3 and x5 are my free variables. So again, I'm going to describe this in parametric form, and then I'm going to describe it in parametric vector form, and then I'm going to take the vectors from parametric vector form, those create my basis for the null of A. So to sum up, the first row says that x1 is equal to negative x3, negative x5. Right? If I take this equation and rearrange it. Second row says x2 is equal to 2x3 and a negative 3x5. The third row here tells me about x4, which means x3 we already know is free, hanging out on its own. x4 we get from the third row, says that this is 5x5, and we know that x5 is also free because it does not have a pivot column. So this, in our vector format, our x vector can always be defined by x3 times the vector -1 for the x1, 2 to get me x2, 1 to get me x3, 0, right, because there's no x3 value in the x4 equation, and 0 again for x5 because, well, they have nothing to do with each other. And then x5 times the vector -1, -3, 0, right, x5 and x3, no relationship, 5 and 1. All right, so the basis for the null of A is equal to the set of those two vectors, of the -1, 2, 1, 0, 0, and -1, 3, 0, 5, 1. All right, there we go. That's it on bases. Well, no, that's not it on bases. We're going to keep talking about them, but that's it for this section.